Hello, my name is Christine Laney, and today I'm going to give a quick talk on the partnership between the National Ecological Observatory Network, or NEON, and the Ecological Forecasting Initiative. My personal work lives at the intersection of science and cyber infrastructure, focusing around data standards and all aspects of fair data. NEON, funded by the NSF and managed by Battelle, is a unique program in ecology. It provides coordinated and co-located measurements of both drivers of environmental change and biological responses. Data are collected at our 81 sites using standardized methods carried out by hundreds of our field staff or thousands of instruments. These methods or instruments systematically sample variability and trends, and the standardized data allow inferences at regional to continental scales. NEON collects data over broad spatial and temporal scales. We have built and now operate 81 sites across the contiguous United States, Alaska, Hawaii, and Puerto Rico. We have partitioned this expanse into 20 ecoclimatic domains. Each domain has a core terrestrial site, a core freshwater aquatic site that is often co-located with the terrestrial site, and one or more other sites that are spatially placed along an environmental gradient. Co-location enables more complete understanding of nutrients, water, and energy through terrestrial and aquatic ecosystems. We will be collecting data for 30 or more years at all sites. Our current data catalog boasts over 180 high-quality data products that are served to our community free of charge. We are also co-located or near to other ecological observing field sites, notably the U.S. Long-Term Ecological Research Network, or LTER, the Long-Term Agricultural Research Network, or LTAR, and the Critical Zone Observatory, or CZO. NEON collects data and samples using a combination of airborne remote sensing, sensors, and field sampling at varying space and time scales. The observatory ingests, monitors quality, and processes data into usable products that are broadly accessible to user communities. The automated instruments provide data that are more easily structured as time series, but are also high volume. Remote sensing, performed with our airborne observation platform, or a suite of instruments mounted on a small aircraft, records enormous quantities of raster and point cloud data. The observational sampling protocols provide a wide range of small, but highly diverse and complex data sets and over 100,000 archive samples a year, including genomic extracts. NEON shares some data products through numerous external repositories to leverage domain expertise to process and share NEON data within a domain context. The NEON data portal provides field data, as well as links to externally hosted data. Distributing data across repositories help ensure that we organize and provide data and metadata in community-supported, domain-specific standards while providing domain communities extra tools of discovery and access. NEON data are free and open through two data portals, one for data products and one for sample records, and through a REST API. These portals and services provide data product information, site information, documents, sample records, and data. Both portals are in active development as user needs become more apparent. We also provide an application programming interface, or API, to programmatically access our data packages, as well as information about data products, locations, our taxonomic lists, and sample records. The API returns information in JSON format, which is widely used and easy to parse. We also provide a GraphQL endpoint, which allows for more refined and custom requests to the API, which is perfect for applications that need to be light and agile. With all this data ready to explore and use in research, NEON has been fortunate to develop a highly valuable partnership with the Ecological Forecasting Initiative, EFI, which is led by Mike Dietz and was launched in 2019 as a grassroots consortium aimed at building and supporting an interdisciplinary community of practice around near-term ecological forecasting. EFI represents a diverse, engaged group of scientists with a keen interest in forecasting ecosystem processes from local to continental scales. In some ways, this group represents different objectives and needs from traditional ecologists, and these align well with NEON's scope and scale. The scientists of EFI brings unique and diverse perspectives to NEON and help inform NEON of how to improve services. Our partnership with EFI has grown over the past 2 years as NEON scientists have become engaged in EFI cyber infrastructure and methods working groups, and with the EFI NEON Research Coordination Network. We'll talk a little bit more on that. In addition, EFI scientists have championed an Ecological Forecasting Technical Working Group at NEON. These partnerships have opened doors to exchanging information about the data and standards that NEON provides and what NEON can do to assist forecasters. The generalized forecasting cycle can be used to highlight the diverse roles that exist in the field of ecological forecasting. The forecasting cycle begins with the development of an ecological model that's designed to be repeatedly executed in a computational environment. That model is then used to generate a forecast. Next, data is obtained from the observational network and compared to the forecast. The forecast is then updated with the observations using statistical analysis so that the next forecast has a starting point that is as consistent as possible with the current conditions and that the model calibration updates through time. The forecasts are archived for future analysis and communicated to the decision maker in a form, like visualizations or web apps, that has been co-developed to maximize utility in decision-making processes. As the forecasting cycle is repeated with many models that differ on their hypothesized views of ecological processes, the successes and failures of the different forecast models help advance our foundational understanding of ecological dynamics. And finally, over time, the successes and failures of the forecast can guide the refinement of the observational network to better constrain model forecasts in a cost-effective way. In view of this generalized workflow, several data needs clearly become evident. First, forecasters need ecological data sets that are available on a regular, frequent basis from natural environments and are fit for use. These data should have a short latency period from collection to publication, and they should be collected using standardized methods within and across many sites in order to help look for higher level patterns across ecosystems. The data need to be provided in consistent formats over time with rich documentation and be programmatically accessible. Manual downloads for forecasting would not be efficient. Forecasters need access to computing environments that will support continual processing of large, often heterogeneous data and trusted long-term storage of computational workflows, including inputs and outputs. NEON can help out with many of these needs. Although we don't supply computing resources, with wide-scale deployment of connected environmental sensors, openly available data, and coordination of observations across large scales, NEON represents a leap forward in the observational capacity necessary to support the continued improvement of researchers' ability to produce ecological forecasts that advance basic and applied objectives. This year marked the kickoff of a new research coordination network funded by the National Science Foundation. The vision of the RCN, a 5-year project, has the vision to solve the challenge of predicting nature and ultimately to forecast the effects of alternative environmental policies and actions. The goal is to create a community of practices that builds capacity for ecological forecasting by leveraging NEON data products. There are multiple objectives that we aim to meet during the course of this RCN. We plan to define community standards and best practices for developing, sharing, and archiving forecast models, and to increase the number and diversity of NEON-enabled forecasts by developing and hosting the NEON Ecological Forecasting Challenge. Foundational to this RCN is creating educational materials to empower scientists at all career stages to forecast using NEON data products, as well as to support the creation of software to produce NEON-enabled forecasts. We also aim to align forecast outputs and decision support with the needs of forecast users at mission-driven agencies to guide decision-making, and to synthesize forecasts to examine how limits to forecastability vary across ecological systems and scales. We held our first RCN meeting May 12th through 13th of this year. Our objectives were to introduce the RCN and the ideas for the NEON Forecasting Challenge, to provide an overview of NEON data, and to identify specific NEON data products to be used in the Forecasting Challenge, and develop a roadmap for the challenge. We also intended to present and discuss standards for archiving ecological forecasts, to identify software and educational needs to empower participation, and finally, to identify partnerships with stakeholders and end users that may leverage NEON-enabled forecasting for decision support. Initially, the workshop was to be held at NEON headquarters with 65 total participants, including 15 graduate students. By going online, we were able to accommodate over 50 students and between 100 and 160 participants total. About 10% of our participants were from outside of the US. Through Through dynamic sessions that balance pre-recorded talks with live question and answer sessions and small engaged breakout groups, participants were able to network with their peers and actively discuss many of the topics that were brought up in the sessions. 5 thematic areas were identified for the forecasting challenge, where NEON data are available regularly and frequently from many sites across the US. This includes, first, aquatic sensors. This includes water quality, discharge, groundwater, and surface water data from freshwater ecosystems, including streams, rivers, and lakes. Second, terrestrial carbon, leveraging NEON surface atmosphere exchange data from eddy covariance towers, as well as soil CO2. Third, ticks and associated pathogens. Fourth, ground beetle communities, leveraging NEON's ground beetle collections, and potentially could tap into archived specimens, bycatch, and DNA sequences of individuals that were difficult to identify in the field or lab. And fifth, phenology measurements, potentially leveraging both our field-collected phenophase and our phenocam data. Discussions centered around these topics and the needs for the challenges have been continued over Slack channels and other forums, and have tapped into our domain experts at NEON. Some of the feedback we're receiving is already informing NEON on where we can assist ecological forecasting work. This includes discovering which of our data products are of highest value for ecological forecasting based on data type, collection, and publication frequency, and accessibility. We're also having useful discussions on the levels of data processing, potentially between raw data that we collect and the data products that we currently provide, that would provide data fit for use and available at frequencies needed for forecasting. We've had discussions on the usefulness of our current data formats and where our file naming conventions need more clarification or need to be more consistent across data products for programmatic parsing within workflows. We are finding efficiencies that could be gained by improving our API structure, and also where we can improve documentation or access to our documentation. So this leads to hopes for the future as we continue our partnership with EFI. We hope to improve our services for forecasters, which would also lead to improvements in services for other end users. We also hope that the EFI community will develop and share code resources and tutorials, which we could expose through the NEON website. Finally, we hope that this will help catalyze the use of NEON data, both within the US and across the globe. While we have seen increased uptake of NEON data, NEON, now in initial operations, is just starting to be tapped, and we look forward to the advances in science to come. Thank you, and we're looking forward to your questions in the Q&A session. Many thanks to the Ecological Forecasting Initiative and to Quinn Thomas for assistance in the preparation of this talk.